So today we're going to be looking at the inverse matrix. So now previously what we've done is we've gone over the determinant, which is a necessary part of finding the inverse matrix, because the inverse matrix includes within itself part of the determinant, and we'll see that as we evaluate it. Now, one of the things with standard algebra and with matrix math, which is also known as, mostly from this point forward, as linear algebra, we're going to refer to that kind of interchangeably, matrix math versus linear algebra, to notate the different notation rules as far as capital variables versus lowercase variables, where in standard algebra it doesn't matter, in linear algebra it does. We'll notice that the inverse of any number is going to be the inverse notated by a power of -1. This is inverse notation. You'll see that a lot in function notation. The same with linear algebra. The inverse of a matrix is shown as the matrix to the power of -1. That means inverse. That does not necessarily mean reciprocal, which you see oftentimes in other scripts. The other thing that we'll notice about is that in standard algebra, it doesn't matter if the inverse of 1, if the inverse is 5 is 1/5. It doesn't matter if I multiply 5 times 1/5 or 1/5 times 5, it cancels out and I get this identity of 1. In linear algebra, we can do the same thing. Matrix times inverse or inverse times matrix, which normally is a big deal, but with the inverse, it doesn't matter which way we do it. We will get the identity matrix, which is shown as this, which is the linear algebra equivalent of a 1. So our question is, first off, how do we check to see are they inverses of each other? So let's start out with some of these and see if we can't spot any rules that we might be going over. So for most of these, we're just going through and we're finding the dot product of the two matrices. So let's take a look at the dot product of these two matrices. If we look at the top row, first times first, that will give us a 2 times -1 is -2. 1 times 3 is 3, which will give us the answer of 1. If I look at the first row in the second column, that will give us a 2 minus 2, which is a 0. And then if I look at the second row, so let's do this. This is my first row, and this is my second row. So I'm taking the first number times the first element of the column, the second number times the second element of the column. So 3 times -1 gives me -3. 1 times 3 gives me 3. Which reduces down to a 0. Then I do the same thing to the next column. 3 times 1 gives me 3. 1 times -2 gives me -2. So we produce the identity matrix. So yes, these are inverses of each other. So take a quick pause and look at it and see if you can't come up with a general assumption as to how we've renegotiated these numbers. And so what you might have noticed is that the 1 and the 2 on our diagonal have been swapped. I now have the 1 up in the top left and the 2 in the bottom right, and they've changed signs. The 1 and the 3 have remained unaffected. So let's see if that holds true to this one. So let's take a look at the diagonal. Yep, the 5 is now up over here, the 2 is now down on the right, and they've changed signs. Negative, positive, positive, negative. The -3 and the 3 have remained unaffected. So our tentative answer is yes, question mark, but let's try it out. So I'm going to find the dot product of the first row. So 2 times 5 is 10. -3 times 3 is -9. Times the second column. 2 times -3 is -6. -3 times -2 is 6. So far, so good. Now I'm going to go with the second row. 3 times 5 is 15. Minus 15, which is 0. Next column, so let's say -9 plus 10. And lo and behold, our answer is yes. They are inverses of each other. So what looks to be the pattern holds true. And so if we try it on the next one, we notice that already I'm looking at this and I'm like, no, those aren't swapped. But let's go ahead and let's try out and see if we can get it, because we'll notice that albeit they're not the exact swap because we don't have fractions over here, I notice that my 8 and my 5 are swapped. They're both divided by 3, which is an interesting question. And my 0 and my 10, well, it looks like I've changed the signs on these, and I've still divided by 3. So my tentative answer is no, question mark. But let's still give it a shot. So I'm going to take the first row times the first column. Actually, we've been doing blue on the second row, but oh well. So negative 5 times that is going to give us a negative 40 thirds plus 0, which is a negative 40 thirds. If I go to the second column, let's see, that's going to give me a 0 plus 0, which is a 0. Go down here. So first column is going to be a negative 80 thirds plus 80. Oh, that was my final answer. It's going to give me a 0. If I go to the next column, that's going to give me a 0 minus, let's see, 8 times 5 is going to give me a 40 thirds. So negative 40 thirds. And so we know that no, our answer is correct, but you might notice that the pattern is the same. I have my two zeros and I have the same number right here. So you might question yourself and say, well, what happens if I unscale this? Well, if I unscale this and divide out my number, I know that this would just be negative 3 over 40 times the identity matrix known as this. And so we ask ourselves, well, can I still produce the identity matrix given a scale? Does a scale have anything to do with that? And we will return to this value later on because the scale is important. We can still have an inverse matrix given a scale. But why don't you go ahead and try number 10. Pause the video, unpause it when you're done, and see how well you did. Okay. So what you notice is, again, I'm looking at terms that aren't swapped and changed. I notice that I have a 1/8 and a 1/2, where I have an 8 and a 2 right here. Yeah, it looks like their signs have been swapped, but not a big deal. Over here, I've got a 1/2 and a 1/4. I've got an 8 and a 4. Not even close to the same thing. Signs look like they've also been swapped. So I'm going to tentatively say, no, these are not going to be the inverse. But we just talked about scales on the previous one. So why don't we go ahead and see if we can pull scales out of these before we even approach it. And so I notice that all of these numbers are all divisible by 2. So what I'm going to do is I'm going to pull out a 2. I unscaled it. So negative 4, 4, negative 2, 1. Basically, I divide them all by 2 so that I can show that I will eventually multiply them by 2. I can do that same trick over here with fractions. If I multiply them all by 8, it would cancel out all these fractions. So if I multiply by 8 on the inside, I'll have to divide by 8 on the outside. Let's see, 8 over 8 is 1, 8 over 2 is 4, 8 over 4 is 2, 8 over 2 is 4. And so lo and behold, what we notice is that yes, now that I've pulled out the scales, these look a lot more familiar. I have my 1s and my 4s swapped, and then I have my 4 and my 2s change signs. So it's not quite the same pattern, but it looks a lot closer to it. So now I might have to change my answer and say yes at this point. Maybe they are. And so let's give that a shot. So the first thing I've got to do is I've got to combine my two scales. So 2 times 1/8 is 2/8, which will eventually come down to a 1/4. now we're going to go ahead and multiply these two matrices. So for the top row, let's do, we've been doing red. We swapped on the last one. Let's stick with red. Okay, so negative 4 times 1 is negative 4. 4 times 2 is 8. So that's going to give us a 4. Second row, that's going to be a 16 minus 16. Perfect. Go for the second row. Negative 2 times 1 is negative 2 plus 2, which is 0. Second column, I get an 8 minus 4, which is a 4. And albeit this isn't my final answer, when I distribute that 1/4 into there, I get a 1, 0, 0, 1. And so we know the answer is, in fact, yes. So albeit it didn't look like it at first, we noticed that the inverse matrix can be hidden behind a scale. So what's the deal with the scale and the inverse? Does it have any effect, and can it be predicted? That's going to lead us to our second part. What we've got going on here is the generalized process on how to find the inverse. And what you noticed is that so far we've gotten really close to what it was. Now there's two ways that we could do this. With a 2 by 2, we can swap and change, or we can swap and change and leave those. We're going to go ahead and we're going to use this one in general. We also noticed that previous topic that we've covered, the determinant, is involved in finding the inverse. 1 over the determinant, or the reciprocal of the determinant, is involved in finding that. So if I want to find the inverse of A, I'm going to take the A term and the D term and I'm going to swap them. And then I'm going to take the B and the C and I'm going to change their sign. So if B was positive, make it negative. If B was negative, make it positive. And I'm going to scale that by the determinant, which is 1 over, in this case, 2 by 2 is AD minus BC. That should produce my identity matrix. So let's go ahead and let's give this a shot. It looks like we've got 4 parts to do here. We want to find the determinant, swap and change, so that we can find the full-on inverse, in which case over here we're going to check to see, does the process work? So for part A, let's do the determinant first. Okay. So the determinant of 13 is going to be AD minus BC, which is negative 5 times 0 minus 1 by 1, which is going to be 0 minus 1, which is negative 1. There's my determinant. I was going to half box it, but there's my determinant for A. If I'm going to swap and change, okay, I'm going to swap this diagonal, which gives me a 0, negative 5, and change the signs to a negative 1, negative 1. So that means the inverse matrix is going to be pushing that value in as a reciprocal into this function. So the inverse itself, let's do this in blue. The reciprocal of negative 1 is 1 over, and we're just going to keep it 1 over negative 1 times this, which is 0, negative 1, negative 1, negative 5. And so now we could show this as the inverse, or I could force that negative 1 in there and say this is equivalent to 0, 1, 1, 5. Either way it works. We're not really concerned with which way you're doing. If you want to say this is the inverse or this is the inverse, it's the same thing. We know that this is equal to this. And so the last part is we have to check to see if this works. So I'm going to take either one of these, doesn't really matter which, I'm going to use this one in this case and multiply it times my original matrix. So let me put this buddy up here. Negative 5, 1, 1, 0, and see what we get. So now I'm going to use the dot product. The dot product we've done before. Okay, so that's going to give me a 0, plus 1, which is going to eventually reduce down into a 1. If I do the second column, 0, 0. Awesome. I've already used blue, so let's use purple. First, that's going to give me a -5 plus 5. The second column, that's going to be a 1 plus 0, or a 1. Yes, in fact, it does check out. This process works. Awesome. Let's try another one together. If I'm looking at this, the first thing I want to find is the determinant, which I know is AD, so 5, 0, minus -1, -2. So 0, that's a +2 made negative, so -2. So the determinant is -2. Awesome. If I want to swap and change this, I'm going to swap this into a 0, 5, swapped that diagonal, and then I'm going to change the sign. In this case, I'm going to have a +1, +2, which means my inverse is one of two things. My first inverse, if I write it as the scale times the inverse, would be a 1 over -2 times this, which is 0, 1, 2, 5. Or I could write it as a 0, -1 half, -1, -5 halves. Both of these are the inverse. It doesn't matter which one you choose. Now, what you might realize is that in our check step, you may use either the full fractions, or you may multiply it by this matrix, which is whole numbers, and then scale it by a half. So that's up to you. What I'm going to do is I'm going to multiply it by this version of our inverse, and then take our answer and cut it in half and change the signs. So if I multiply by our original matrix, which is 5, -1, -2, 0. Okay, it's going to give me I'm eventually going to scale this by -1 half. But I'm going to multiply this matrix times this matrix. And again, because we've already used some of these colors, top row is going to be red. So first, 0 times 5 is 0. 1 times -2 is, which is -2. If I go to the second row, 0 times 1 is 0. 1 times 0 is 0. Okay. So first, that's going to give us a 10 minus 10. In the second row, first is going to give us a -2. Plus 0. -2. And if I force in my scale at this point, I will get a 1, 0, 0, 1. Yep, that checks out. Now, the only reason why I use the original inverse right here is because it leads us to finding dot products of whole numbers. You don't need to. I could have easily used this, but again, fractions, not that I'm trying to avoid them, but oftentimes we like to avoid unnecessary complications. So we've got a few left. Let's go ahead and try number 17. So let's give number 17 a shot. Pause the video, unpause it when you're done, and see how well you did. In fact, try 17 and 19. Try both of them out, and we'll work both of them here shortly. Okay? So let's work these in tandem. On number 17, we're finding the determinant. So AD, 2 times 0, minus -2 times -2. So 0, that's a positive 4. So if my determinant is a negative 4, what that means is the scale that I'm going to be multiplying this is a reciprocal of that by a negative 1/4. But our next step is to go ahead and do the change and swap. So I'm going to take this and I'm going to swap these two, so 0 and 2, and then change those to a positive 2 and a positive 2. Now this means that my inverse is either going to be my scale and my swapped matrix, so a negative 1/4 times this thing, so 0, 2, 2, 2. I have that as a possible option for my inverse. Or I could force in that scale and say it's a 0, let's see, negative 2/4 is negative 1/2, negative 1/2, negative 1/2. So you have two options. Both of these are your inverse. You can pick whichever one you like, and these are going to be what you're going to multiply by to completely undo this matrix and create an identity matrix. So let's go ahead and let's work this time. Let's work this one. Just get a variety of what we are seeing under our belt. So I'm going to take the right one and I'm going to multiply it times our original matrix of 2, negative 2, negative 2, 0, 2, negative 2, negative 2, 0, and see what we get. So I'm going to go ahead and I'm going to take the top row. So I'm going to go ahead and do this. So dot product is going to give us so dot product right here is 0 times 2, which is 0. Negative 1/2 times negative 2 is going to be plus 1, which is 1. I do it to my next column, so 0 times negative 2 is going to be 0. Negative 1/2 times 0 is 0, so we get that. Let's see, and we did purple for the second row. So let's do this second row of dot products in purple. So first, so negative 1/2 of 2 is going to be negative 1. Yeah, negative 1/2 of 2 is negative 1. And then we do half of 2 is going to be, negative half of 2 is 1, which is going to reduce that to a 0. Then we do the second column, so negative 1/2 of negative 2 is 1, plus 0, which is 1. So we see the fact that it actually does, no matter if we do what we did previously, where we took the non-scaled version and multiplied it where it took 1, 2, 3 steps, or if we use the scaled version, which just took 1, 2 steps, they both work out to be the same thing. So it's really a matter of personal preference. Do you want to deal with whole numbers or do you want to deal with the fractions? Really, I think it boils down to how many questions you've done that day or in that set. The more you've done, the less I would really want to work with the fractions because they are very prone to casual mistakes, but they're doable. So number 19 was the other one that you tried. So let's go ahead and find the determinant, which is going to be 0 times 5 minus negative 5 times 2. So that's going to be 0 plus 10. My determinant is 10, which means I'm scaling that matrix by 1/10. I do my swap and change of 5, 0, make that a positive, make that a negative. And that leads us into our choice of which matrix do we want to pick. Do we want to pick the scaled version, which is going to be 1/10 times this, 5, 5, it's a negative 2, 0. Or do we want to pick the forced in scale version where we say, okay, let's take 1/10 of all this. So 5/10 is 1/2, 1/2, 2/10 is negative 1/5, 0. Cool. Regardless of which one you picked, if you picked the one without the scale forced in or the one with it forced in, you're going to multiply it times the original of 0, negative 5, 2, 5. Okay. I think we are again going to use the fractional form for this example. We're going to use the top row, so the dot product, half of 0. Actually, let's set this up. So half of 0 is 0. Half of a half is 1. As we move to the second, half of -5 is -5 halves, and half of +5 is +5 halves. Those two terms cancel out. Second row, first column, 1/5 of 0 is 0. 0 of 2 is 0. -1/5 of -5 is 1. 0 times +5 is 0. So it checks out. Perfect. Okay. So now that you've seen 2 in action, there's really only 1 left. Why don't you go ahead and try number 21. Pause the video, unpause it when you're done, and see how well you did. Okay. So let's knock through this one. We find a determinant, -2, -3, minus -3, 0. Cancels out, it's a 6. Swap and change. -3, -2, 3, and changing the 0 is just a 0. And that's going to lead us to our choice of which one do we want. Do we want to take the 1/6 and leave this? Or do we want to force that 1/6 in? -3/6 would be -1/2, +1/2, 0, and 2/6 is -1/3. You have your set of choices. -2, -3, 0, -3. Okay, so what I think we're going to do this time, because we've done 2 in a row where we've used the forced in version, let's go ahead and use the non-scale version. So this is going to take 3 steps. Because we know out front I still have the 1/6. So let's use the red. So row 1, column 1, -3 times -2 is 6. 3 times 0 is 0. I do the second row. -3 times 1/2 is -3 halves, 5/12. And let's see, 1/6 times that is going to be 2/18, which is 1/9. Yeah, this does not. Okay, so what I was trying to do earlier was I had mixed my matrices up as I was multiplying this times this originally, and then I kind of migrated over to multiplying this matrix. So my answer fell apart. So let's ignore what just happened right there, and let's go back to multiplying original times that. Probably not recommended because we're going to have to cover up this matrix because it is muy distracting. Boom, there we go. Can't get distracted by what we can't see. So what we have going on is we're going to take our first matrix, and we know that that 1/6 is going to stay on the outside. So 1/6, 1/6, and that will eventually give us our final matrix. But we're going to take our top one, so it's going to be a -3 times 2, which is 6, and then we're going to take our 3 times 0, which is 0, so 6 and 1/6 of 6 is 1. We're going to move to the next column, so -3 times -3 is 9, and then 3 times -3 is -9, which gives us a 0 all the way down. And then we're going to move to the purple, so the second row, so 0 times 2 is 0, -2 times 0 is 0, 1/6 of 0 is 0. Last up, 0 times -3 is 0, -2 times -3 is 6, 1/6 of 6 is 1. So we see that this does check out. And there we go.